Right, in section 2.2, we started talking about set operations, and we're going to look at some, or we talked about some set operations. We're going to look at some other set operations today and their properties in section 2.3. The first set operation we're going to look at is the idea of a set intersection. So a set intersection is a way of looking at sets to see what they have in common. Okay? So the phrase you should be thinking about when you think about intersection is what they have in common. Another way to think about it is to simply think about what we mean by the word intersection. So when you talk about the intersection of two lines, you're talking about the place they cross. When you're talking about a street intersection, you're talking about the location where those two streets actually cross one another. All right? So the same thing true for sets. It's where they cross what they have in common with one another. So the notation that we use for that is an upside down U. Some students have told me before they like to think about that symbol as looking kind of like a lowercase n or intersection. So that would work for me. And I'm going to show you the set notation for how this looks as well. This is the set of all x, such that x is an element of A, and x is an element of B. All right, a set union is a set of elements where the elements are in one set, the other set, or both. Let me show you the union notation, and then we'll talk about how we sort of think about union. So this is the set of all x, such that x is an element of A, or x is an element of B. It does not need to be element of both of them. Either one or the other is fine. If it does happen to be an element of both of them, so much the better. It gets included as well. When you think of union, I want you to think of what happens when people get married. They talk about that being a union. You've heard that phrase before, right? What that means is it means that everything that's yours is now mine, and everything that's mine is now yours. Right? You get to collect all of it. It means you get all the extra money, and you get all the extra debt. Right? It means you get all the good stuff and you get all the bad stuff. It's a union. You collect it all and you combine it all together. Okay? So a union is a combination of everything that once was separate into one big pile now. Okay? An intersection is what was already in common to both. Relative complement or difference, sometimes people call it the difference, is the set of elements in one set that are not in another. So the reason it's called difference is because it actually looks like you're subtracting. So A minus B means the set of all x, such that x is an element of A, and x is not an element of B. So it's in the first set, and it is not in the second set. It is removed from that. So I think a picture of each of these is helpful. So I want to start by drawing a picture to represent these, a visual argument. And we will draw these, I'll just draw them out by hand. We're going to draw these as Venn diagrams. So if we have two sets, we're going to draw them as two circles. One set we're going to call A, the other one's B inside of my universal set U. And I'm going to draw that same picture in all of these. The part that's going to be different is what I shade in. The part that I shaded is going to represent the operation that I'm sort of describing. So the first one, the set intersection, means what they have in common, what's in both sets. Where is that in this picture? Yeah, so this sort of football-like shape here in the middle, right, Taylor? This is the intersection. It's the part where they overlap. That's what an intersection is. It's the overlap. Right? Again, we can sort of think about this as when I'm talking about myself and my husband, we have interests that overlap, and we have interests that don't. That's actually how my daughter was first introduced to Venn diagrams when she did these in second grade, is that she and a friend were putting things that overlapped, that had in common in the middle, interests that overlapped. But because we're not like 100% any other person, there are going to be pieces that don't overlap. right? We are different people. So if we're looking at the union, I'm supposed to be in one set, the other set, or both. What part would be shaded on this diagram? Well, I'm supposed to shade everything inside circle A, right? So I would go and shade everything in here. And I'm also supposed to shade everything inside circle B. Well, a portion of circle B is already shaded in. So I don't need to shade it again, but it's already shaded in. But I also need to shade in the additional part of circle B that hasn't already been shaded. There are my interests, there are my husband's interests, and then there are things we have both in common as far as our interests are concerned. We get it all when we're talking about the union of our interests. Difference, same picture to start with. But what this one says is that I need to be inside of circle A and not inside of circle B. Where is that? It's like the left side, right? It's the outer part of circle A. So it's just this sort of crescent moon-looking shape out here that we're referring to. Notice, it doesn't say anything about anything being in B. I don't care what's in B. I just need to not be in B to remove that portion of B from my argument. I'm going to do an example of these so that you can kind of get a sense of how this works when you have a set defined instead of drawing a picture for it, okay? Are you guys ready to take a look? All right, let's see if I've got it all written there correctly now. Consider Mary, single mom of one child, Mark. Yeah, there's a typo. I think I left it on purpose. And then Joe, a single dad of two children, Jack and Jill. Mary and Joe get married. Put Joe here. All right. Mary and Joe get married. And then together they have two children, Anne and Andy. If M equals Mary's kids and J equals Joe's kids, find the following. All right, so we're talking biological children here so that we can make the argument that we're looking at, not how they feel about them emotionally or anything like that. I get it, they're all children, I get it, all right? But we're going to take a look at finding M intersect J, at finding M union J, and finding M minus J. Okay, so the first one says intersect. So what is it that we're looking for if we're looking for the intersection? The two kids they have in common, or the kids they have in common. In this case, it is two kids. What two kids do they have in common? Anne and Andy, right? Okay, that's the intersection. That's where their kids coincide. The kids they had together. What does this look like? Union, M union J. What does that look like? It's all the kids combined. It's the family picture point of view, right? It's who would get to be in the picture if we included everybody. So who would that be in this set? Mark, Jack, Jill, whoops, Anne, and Andy, right. All right, let's do M minus J. So M minus J, what would that be? It would be what? It would be just Mark, exactly. So it needs to be Mary's kids. Well, Mary has 3 kids actually, right? In this argument, who are her kids? Mark, Anne, and Andy. So we only start with Mary's kids. That's what this A at the beginning means. It means that's the only people we're considering. And then we're supposed to remove what? Any of those kids that Joe had in common with her, right? So that's why Anne and Andy get removed. In this argument, this is left with Mark. Can I get a sense of what's happening here and how to work with them in an example? I think I have another one. Oh, not yet. We'll do another one in a minute. Okay, let's take a look at commutativity. The commutativity of sets and intersections, of set intersections and set unions. Notice when we are talking about two sets doing the intersection of them, it doesn't matter the order we do the intersection, right? If I intersect A with B, that's the exact same thing as intersecting B with A. It's commutative. Commutativity is the ability to change the order around. And the same is true for the set union property. If I do the union of A and B, it's the same as doing the union of B with A. No difference. And this works for all sets A and B. Order doesn't matter. Associativity is a little bit different. Associativity says that if I have A union B union C, so I have to have three sets to talk about associativity, that I can do regrouping. I can reassociate the different sets together. That is, I can take the parentheses where they are and I can move them from being around B union C and put them around A union B. Right, so if I look at what B and C have all together, and then I consider that set with everything that A has all together, it would be the same as looking at the set A and B all together, and then including the set B in that discussion. And this works with set intersections as well. I guess I kind of did this out of order for what I had written down, but it's the same thing. So if I do the intersection of B and C, and then I intersect it with A, it's the same as doing the intersection with A and B, and then intersecting it with C. Same thing. The last one is a combination of sets and intersections and unions and how they interplay with each other. I should say that this is for all sets A, B, and C. All right, so the way that these interplay with each other is that if you're taking the intersection of A with the union of B and C, this is the same as taking the intersection with B and the intersection with C, and then taking their union. Do you see that distribution property that you've seen ages ago somewhere in elementary school, probably the first time, or middle school? And you sort of distribute the A intersect B, the A intersect to the B, and the A intersect to the C, right here. And then the union that was between them is now between the two sets intersected. Again, this is for all sets A, B, and C. Now we could actually prove that these work. In particular, this last one's quite interesting, although the middle one works nicely as well. We can prove these work by actually taking a look at what a Venn diagram would look like if we did the stuff on the left-hand side, and compare it to what a Venn diagram would look like if we did the operations in that order on the right-hand side. And we would find that the two Venn diagrams would match in the end. And we're going to take a look at how those Venn diagrams work. We've got one more slide before that. But work can work in actually showing those things to be true. That's where we're headed. So one more step before we get there. We're going to talk about cardinal number in Cartesian product, I guess. All right, the cardinal number formula says the following. If I would like to figure out how many items are in an intersection, a union, the number of items in the union, what I could do is I could take the number of items in set A, and I could take that and add that to the number of items in set B. And I'm going to run into a problem if I do. So let me show you what this has so far. It's incomplete as drawn. But let me draw a picture to argue why it is what's going to happen next. All right, so we already know what happens when we look at the intersection and the union of sets in a picture point of view. So I know that if I were to shade in all of the A union B, I'd be just shading in everything inside the two circles, right? We talked about that on the previous slide. So what if I want to shade in the number of items in set A? Well, this piece right here, I'll shade it in red, would be everything right here. This would be everything included in set A. Right? So anything in the outer part of A, anything in the overlap, both of those would be in set A. If I shade everything in set B, it would look like this. Right? The problem is what? They overlap. overlapped, I double shaded a portion of this, right? So if I counted everything out here in circle A, and I counted everything in circle B, then the things in the overlap got counted twice, didn't they? Right, like if we go back to Mary and Joe and their kids, and we counted all of Mary's kids, and we counted all of Joe's kids, Ann and Andy would have got counted twice, wouldn't they? So how do we take care of that? Well, we actually remove one of the double countings. So we remove one time, not twice, because then we would remove everything in the middle section. We just want to remove the double counting in the middle section. Excuse me. So we subtract off the number of items in the intersection one time. And that would work back in Mary and Mary and Joe's case over there too, right? So if you had Mary's kids, I think she had 3, right? Because she had Mark and then she had Ann and Andy. She had 3 kids. And then Joe had 4 kids, right? Jack, Jill, and Andy. And if you add the 3 and the 4 together, you get 7. There are not 7 children, right? How many children are there? There were 5 children. Exactly 2 too many. That's because I counted Ann and Andy twice, right? So if I were to remove those 2, one of the double counts, then I would actually get the number I'm working with. Cartesian product is the last type of operation in this section. And I think if I want to do that first, or if I want to do your Venn diagrams first. I'll just keep it in order of what it's got so far. That's all right. All right. The Cartesian product is the set of all ordered pairs, such that the first component comes from the first set, and the second component comes from the second set. This is similar to the question, Audrey, that you asked me about, where we had I plus j, and we had I coming from the first set, and the j values coming from the second set, and we combined them in some way. We're combining them in a different way on here than that particular problem, but that problem had some similarities to it. The Cartesian product looks like a product, like a cross to it, like this. And what the Cartesian product is that it is the set of all ordered pairs, like this. Actually, it looks like a point in a plane, right? An XY point. This works such that X is an element of set A, that is the first item is an element of the first set, and Y is an element of B. That is the second of the 2 ordered pairs is an element of the second set. And I want to do an example so you can see how this actually works if you're actually trying to create one. So let's say for a moment that we have set A, and it is, let's do the numbers 1, 2, 3. And we will do set B, and just to make it distinctive, we'll actually let it be letters, just for something different. And let's say it's the letters H, K, M, and S, for no particular reason at all. And then what it means to do a cross product, Cartesian product, is that we make ordered pairs of this information. So we take one item, we'll do the first item from set A, and we write it as an ordered pair with the first item from the set B. And we can take the first item from set A and write it with the second item from set B. Running out of space. We can take the first item from set A and write it with the third item from set B, and the first item from set A and the fourth item, from set B. This is all of the combinations of the first item, number 1, with the letters in set B. Made a bunch of ordered pairs. But there was nothing special about using the number 1. These are also drawn inside of a curly brace. I just am out of space, so we'll try. So we could have used the number 2 with H, 2 with K, 2 with M, or 2 with S. All ordered pairs. But again, nothing special about 2. We could have done 3 with H, or 3 with K, 3 with M, or 3 with S. And this would be the collection of all of these ordered pairs where we combine this notation of everything in set A, one by one, with everything in set B. I'd like for you to notice something interesting about what's going on here, though. I don't think I mentioned it later, so I think probably here's a good spot for it. Yeah. How many items are in set A? Okay, good. What's the cardinal number? How many items are in set B? How many items are in the Cartesian product? That is, how many ordered pairs do I have? 12. Any conjecture about the relationship between those? Yeah. And there is a cardinal number formula for this as well that says the number of items in set A cross B is equal to the number of items in set A times the number of items in set B. This is a multiplication times symbol there. It's not the same x that's right here. This does not say that A cross B equals A and B. It's saying the number of items do, right? In fact, none of these items are the same. Nothing from set A is actually an item in set B. It's just the counting them up of what's there. There are 12 items here. There are 3 items in set A. There are 4 items in set B. So there's a relationship between how many items are in each of the sets. Do you guys see the distinction? Sets are not the same, but the number of items are when you multiply them. All right, you ready to take a look at some Venn diagram discussions? I think these are interesting. I think we have time for at least one of them anyway. All right, the first one we're going to look at is this. This isn't on your paper yet. We're going to do A with the complement bar on top. And we're going to do the union of B with the complement bar on top. And there are multiple ways to do what I'm going to show you how to do. I have not always learned or taught it the way that I do, but the reason I teach it this way is because it seems to reach the most people. It seems to resonate the best. I actually had a student show me this after I was teaching it a different way, and I thought, well, that was really nice. I really like that, and I've taught it that way ever since. So when we're working with the Venn diagrams, we're going to start by drawing a rectangle. And then we're going to draw circles for however many different sets we're talking about. So I have 2 sets here, A, B. So I need 2 circles, and they're going to overlap. That's what I want to do. We're going to call one of them A. We're going to call one of them B, and we're going to put a U on the outside. This is where I'm going to deviate from what I would have done years ago into what I do now. What I'm going to do is I'm going to put numbers in each one of the areas of my picture. Okay? So if you'll put your numbers in the same spot as mine, it'd probably make it the easiest to follow. I'm going to put a 1 over here in the A part. I'm going to put a 2 in the overlap. I'm going to put a 3 in the part that's the B only, and I'm going to put a 4 on the outside. This doesn't mean there's 1 item, 2 items, 3 items. They're just labels. I could have used letter labels just as well. So I'm just using these to sort of designate a space or an area of the graph. Everybody good with that so far? I'm going to use numbers differently next time. Right now, these are just designating a location. What we're going to do is we're going to consider these locations based on what the information is we're looking to find. That is, I'm going to look at my diagram with the numbers in it, and I'm going to decide which of the numbers, as listed, are in A complement. Okay, so remember, A complement means not in A. So which of these numbers are not in A? 3 and 4. It's really important. Did everybody see where the 3 and the 4 came from? Great. We're going to do the same thing again because the other piece says B complement. So I need everything not in B. 1 and 4. Everybody good so far? Then what I'm supposed to do is I'm supposed to combine these, sort of like adding or subtracting or multiplying or dividing. I'm going to combine them with whatever symbol it is that I'm being told to combine them with. In this case, the symbol is a union symbol. So think with me, union. Do you get the part they have in common, or do you get the whole thing? You get the whole thing. So when I'm looking at union, I'm looking at the numbers that have been listed, And I'm going to write down that A complement union B complement should be all of these numbers, which would be the numbers 1, 3, 4. Now this is the work, but this isn't the answer. The answer is supposed to be a shading of the diagram, right? So I come back over to my shading and I shade the regions that I labeled with 1, 3, and 4. And that is the Venn diagram representation for A complement union B complement. Now pause with me, I know we're out of time, but pause with me just for a second and think about that it makes sense. This says I want the union of everything not in A, which would be everything outside of circle A. I want that to be joined with everything outside of circle B. The only thing that wouldn't include is the overlapping part in the middle. So it should make sense when you're done, especially working with the two cases where there's just two circles, to be able to look back and say, yeah, that's reasonable. Okay, all right, so we're done with this half of the section. We'll finish